Welcome to ATMOS 5000 Day 12. We're focusing in on Chapter 4, Section 4.5 of the Stull textbook. The topic for today is water budget in an Eulerian framework, and specifically we'll be looking at how horizontal advection, precipitation, and moisture fluxes due to turbulence will impact the total water mixing ratio in a given air parcel at a given location. Here we have the water budget equation in an Eulerian framework taken from the Stull textbook. The term on the left is the storage term at a given location. It's the change in the total water mixing ratio over time. And on the right, there are three terms that can impact the storage of water at a given location. The first is horizontal advection. The second is precipitation, and the third is turbulence. And what we're going to do is we're going to look in more detail at each one of these terms to see how they operate and how they will impact the total water storage at a given location. Here we have the horizontal advection component of the total water storage equation. It looks very similar to the temperature advection that we had seen previously, essentially minus U delta RT over delta X, where delta RT over delta X is the east-west gradient of the total water mixing ratio, and U is our east-west wind. And then it would be minus V, which is our north-south wind, times the north-south gradient of the total water mixing ratio, delta RT over delta Y. On the left, we can see that we have a gradient in the total water mixing ratio, RT, that is increasing as we move from left to right across the page. That is our X direction. So that means that our delta RT over delta X is greater than 0. And then if you look on the up-down direction, which in this case is the north-south direction, you'll see that the total water mixing ratio is decreasing as you move north. So delta RT over delta Y is less than 0. If we have a wind that is shown in the green arrow, that one has a positive U component and a negative V component. So if we put this together, the first term, the minus U delta RT over delta X, the U is positive, and the delta RT over delta X is positive, but we have a negative sign out in front, so that component of the term is going to be negative, which will cause a decrease in the storage of water at that location. If we look at the second term, our V is less than 0, and our delta RT delta Y is less than 0, so that would be negative times a negative, which would be essentially a positive, but then we have the negative out in front, so this term also is producing a negative water storage. So overall, the wind is bringing in air with a lower total water mixing ratio, not a total water vapor mixing ratio, but a total water mixing ratio. Therefore, RT will decrease due to horizontal advection for these conditions. Next, we're looking at precipitation. The water storage due to precipitation is essentially the density of the liquid water divided by the density of the air times the change in the precipitation rate, PR, divided by the change in height. So essentially it's PR at height 1 minus PR at height 2 divided by height 1 minus height 2, delta PR over delta Z. So over on the left, we have a cloud which is raining, and it's a cloud base is essentially kind of 2 kilometers above the surface. The rain is falling out of the cloud, but not all of it is making it down to the surface because some of it is evaporating on the way down. This is very common in Utah when we have high base thunderstorms, and we refer to this as virga if none of the water is reaching the ground, but in this case we do have water reaching the ground. So the question that we have is, will these precipitation rates increase or decrease the water storage in this area underneath the cloud. So what we have to do is we have to determine the sign of delta PR over delta Z. So if we look at the precipitation rate immediately coming out of the cloud, it's 9 millimeters per hour. And as we move down 1 kilometer, the precipitation rate decreases to 7 millimeters per hour. And as we move down to the surface, the precipitation rate has decreased to 5 millimeters per hour. So in this case, the precipitation rate is getting bigger as you move up in the atmosphere. So in this case, that would imply that delta PR over delta Z is greater than 0. In essence, what you have is you have more precipitation falling into the volume than is exiting out the bottom. And therefore, the total water mixing ratio, RT, will increase because more is coming in than going out of the box, essentially. Turbulence is one of those things which is really difficult for us to deal with quantitatively. But let's take a look at the figure on the left to kind of define the situation that we have. So over here we have the vertical axis is height, and we have the convective mixed layer shown in brown, which is typically anywhere from 1 to 5 kilometers high, depending upon time of day and location. And then we have the free atmosphere above, which is shown in blue. If we look at the potential temperature in this layer, which is the red line, the potential temperature of the air is typically highest right near the ground because that is where the sun is warming up the ground, and the ground is warming up the air by conduction, the air directly in contact with the ground. And then the air is becoming well mixed within the convective mixed layer or the boundary layer. And in a well-mixed boundary layer, the potential temperature, theta, will be constant with height because you're mixing all the thermodynamic properties together, and that's essentially the result that comes out of a well-mixed situation. And then at the top of the mixed layer, or top of the boundary layer, we typically have a capping inversion where the potential temperature increases sharply with height, followed by a gradual increase in potential temperature. That's very common. In contrast, over on the left side, we have this green line, which is our total water mixing ratio. And for the most part, the free atmosphere is fairly dry compared to the surface for most surfaces. And in general, the flux of water from the surface due to evaporation is going to dominate this scenario. And in this particular case, we have a flux of water vapor from the surface to the environment, and that is raising the water vapor total water mixing ratio near the surface, and then that's getting mixed as we move up into the atmosphere. And then we have a sharp decrease in the total water mixing ratio at the top of the boundary layer, followed by the relatively dry conditions in the free atmosphere. And for this argument, or for this scenario, what we're going to do is we're going to define the flux of water vapor at the top of that boundary layer. So FZ turbulence at the top of the boundary layer is going to be 0.05 grams per kilogram per times meter per second. And that it means that we're transporting water vapor out of the convex mixed layer into the free atmosphere. And at the surface, in this scenario, we're going to have FZ turbulence is going to be 0.08 grams per kilogram meter per second. And what that means is that we do have evaporation from the surface. And what we have here is the situation is that the change in the flux in the vertical direction due to turbulence is decreasing as we move up away from the surface in this scenario. So our delta FZ turbulence divided by delta Z is going to be less than 0. And in the turbulence equation up at the top, you can see that the water storage is actually governed by minus delta FZ turbulence over delta Z. So in this case, we have more water that is evaporating into the boundary layer than is exiting through the top of the boundary layer through the process of entrainment. And therefore, the total water mixing ratio will increase over time because we're evaporating more than is escaping through the top of the boundary layer. And that's actually a fairly common situation.